Hello, everybody. I'm Matt Berger. I'm with DriveSavers Data Recovery, and I work in the Flash physical department. So that is anything that's non-rotational media, so not magnetic storage. So anything as small as a flash drive, all the way up into any sort of RAID system that uses SSDs that are part of that. That's what we're going to be responsible for. That department has come a long way in the last few years. DriveSavers started about 40 years ago. And back then, all the data was stored on hard drives, floppy drives, really small storage devices that were what they had at the time. But now think about it. Everybody's data is stored on your phone, your MacBook, everything NAND Flash. And just something interesting about that is that in 2020, it was the last time Apple shipped a computer with a rotational hard drive in it. Everything you can buy from Apple at this point is going to be solid state NAND Flash. And so there's going to be a move of user data where obviously there's still RAID systems, there's still 156 drive helium drive systems that corporations are using, but by and large, user data is going to be on NAND Flash. This is a trend that we're seeing across all of the main consumer electronic device companies, Samsung, Apple, the big players. And so today we're actually going to talk a little bit about no recovery scenarios. First, we're going to talk about fraudulent storage devices. If you run a repair shop, I'm sure you've seen them. The flash drives you can get from Amazon that claim to be several terabytes, they're a little too cheap. They're in that classic housing that you see a flash drive in that's direct from China. We've all seen them. And then we're going to talk about degrading flash storage. So NANDs do degrade over time. Just like anything, with use, you're going to start to get less and less use out of it. And we're going to talk about why that is. NAND Flash actually came out in 1987. So it's not as new as a lot of people think. And we're seeing now an onset of aging flash devices. And they will eventually wear out, just like all storage devices. Then we're going to cover some challenges with recoveries in terms of new fast SSDs. Some of the SSDs that manufacturers are putting out are incredible. They have amazing speeds. But what they do in the firmware to make that possible can't be detrimental in a recovery scenario. We'll go over why. And then lastly, we're going to talk about how
Some of these things we plan to change into possible recovery scenarios.
So let's just go ahead and start here with fake flash drives. Most of us have seen them. And if you haven't, you've gone online and you've seen people have said, I got scammed with a flash drive that said it was however big, it deleted my files aren't on there, or it's not letting me put files on it. So I decided I would locate one of these, which they're pretty easy to locate on all the online marketplaces, and try to see how it works. And this is what I came up with. It is reportedly a 2,000 gigabyte flash drive. It's pretty large for a USB 2.0 flash drive. It's from a seller on Amazon that was not fulfilled through Amazon, just some independent seller. And here's some of the details in the listing that I took from the screen. The listing has since been taken down, but here's some of the details. Large capacity storage USB flash super space. So that's instilling confidence already in the first listed spec. We have plug-in works. The drive has simple plug-and-play design without any software installation. I would say not any software installation that you know of when you plug it into your computer. There may be some going on in the background for some of these. And then they tout all kinds of resistance there. We have water, magnetic, high temperature, X-ray resistance. And I took that one as sort of a personal challenge. And so I decided to do this and get a look inside of it. And there's a few things we can tell from this 2,000 gigabyte flash drive. It has a BGA 152 type NAND chip, which is pretty standard. The controller is actually very small. It's right there in the middle. It's pretty small for a 2 terabyte flash drive. And it's kind of amazing that you can go online and see all these features and reportedly get it for $12.99. So it sounds like an amazing deal to me. And I decided, let's plug this into some systems and see what's actually going on with this and why this wouldn't be something that you should put your data on and expect a full recovery. When we connect the drive to a system, this is what it claims it is with the ID from the drive. We have a pretty generic model. We have vendor code, product code. Then it says firmware version 2.0, which I'm glad they decided to revise it at some point. That's very nice of them. And it shows that it has 4 billion sectors of 512 bytes. So it's reporting to be the size that it says it is. And I thought, well, how does this really work? There's no way this is real. There's a lot of these. You've probably seen videos online of how these work. Some of them write over themselves. Some of them have firmware where the data is just not going anywhere. This one individually was actually pretty interesting. But what I did was I wrote a pattern to the drive in hex that labels what each logical block is by number. You can see it there on the right side in the plain text. So once we got to about 58 gigabytes of sectors, the sectors mysteriously stopped being written, just turned into nothing. So any sector after 122,243,071, it just becomes nothing. It becomes zeros. So if you filled up this drive and then you want to add a new file to it, there's a custom firmware on this drive that essentially is going to write that file that you put into the front of the drive at the master file table. It's going to show up in your Explorer, your Finder on your computer. You're going to see the file there, but part of it, or not, maybe all of it, if it's past that limit, is just going to be zeros. So there's no data there. The actual file isn't anywhere. So going without saying, or goes without saying, this is an unrecoverable scenario. If you filled up that drive to that limit on this fake drive and then put a very important file on it, it may show that it's on this drive, but this particular one is not writing it anywhere. It's just going to be blank. This isn't how all these drives work. Each company that makes these fraudulent devices has sort of a different scheme for doing it. Your experience may vary if you come across one of these, but these are the kind of things to look for. And move on to NAND degradation. Degraded NANDs are something that are becoming more prevalent the more prevalent flash devices get. And even truly high quality drives will eventually fail. A SanDisk, a Western Digital, any of that will eventually fail. We see drives that get used day in and day out for years, and then they'll eventually not be able to be accessed by the end user. I just want to go over why that is. This is a little chart I've prepared of how a NAND gate cell actually works inside of the drive. As you can see, we have on the top, there's the control gate that controls it. Then we have an oxide layer. That's the oxide in these cells etched into the silicon is acting as an insulator. Then below that, we have the floating gate. That's where the actual charge is stored that is then turned into the data. Then there's another layer of oxide. Then on the right and left side, we have the source and drain connections. Then we have the channel underneath, and it's attached to the substrate, the rigid substrate that's like the silicon bottom layer. The oxide in this scheme is very important because, again, it's the insulator between places that electronic charges are held and where they go. The floating gate alone can have, it says 10 million volts per centimeter, which is incredibly high for an electrical charge, and this generates an electrical field. That electrical field is so powerful for such a small chip that eventually it will actually start to break down the oxide at the atomic level. So it starts failing. And then once that insulator is broken down, the electronic charge that's stored in that cell can start to leak to other places. And it can't be used anymore. This is pretty normal. This is normal operation of a NAND. Eventually, if enough cells fail, the first few, you're going to be okay. Your drive can compensate. They're made to do that. But it's okay until it isn't. You cross a threshold. So the controller will start to have a hard time with working with that storage media once you reach a certain threshold, and you may lose access to the drive when it's plugged into your computer. Eventually, you may find yourself in a potential data loss situation. We see people all the time who say, well, it was working a little bit, it got slow, and now it's not connecting to anything. When the drive starts to have this type of issue, it depends on how severe the media damage is, but there are several steps before it becomes a no recovery scenario. The least extreme case is going to be sort of two categories. One, we could extract the data through the controller using hardware imaging, and it may have some errors we can compensate for, or maybe some errors that you can't compensate for. But either way, you're still gaining access through specialized hardware that can work with that controller in a different way than your operating system can. Or two, the actual NAND has degraded to the point where there's a firmware failure. And then you have to inject a custom firmware into this drive, and you'll be able to extract data off of it. But a lot of times that's going to contain a lot of media damage because, again, these NANDs are starting to become degraded. With degraded firmware, it's just worth noting that you can start to see strange behavior from the drive. If the firmware is degraded, the drive's still sort of operational. You're plugging in your computer, the firmware can start to do weird things. And that's when it'll start sort of fail itself. The next and more advanced method, once you go past those sort of easy scenarios, is going to be taking the NANDs off and dumping the raw data off of them, just the raw ones and zeros that are on the chip, and then using software with a series of mathematical operations to reconstruct those ones and zeros, how the controller of the drive would reconstruct them to turn it into usable data. Essentially, you can see on the right here, we have a graphical representation of how we'd be looking at those ones and zeros when we're working with it in that way. The red pixels being a 1 and the black pixels being a 0. So that's a graphical representation of what this data on a NAND might look like. It's pretty common to view it that way. And unfortunately, if the raw data on the NAND it has a bunch of errors that can't be compensated for, eventually it'll become too prevalent, and you may, in some scenarios, not be able to get what the customer wants off the drive. You could get maybe things that are not as damaged, but it's not the data that they're going after, or you won't be able to get any usable data at all. And in that period, it becomes a no recovery. This is a pretty common scenario we're seeing with older flash drives, older SSDs, things that have NAND technology that's a little more antiquated, which is a strange saying about NAND Flash, but it is a very common scenario. Next, we're going to talk about SSD deletion. Deletion recoveries are common for a whole wide variety of scenarios, but with SSDs, and especially the new fast SSDs, it's substantially different than with a hard drive. With magnetic recording, it can overwrite itself by simply going over that spot and writing new data to the surface that it's recording to where the old data was, just simply overwriting. SSDs can't do that. They need truly empty space in the cells to be able to write to. And if you want a drive to write fast, like all these manufacturers do, you have to have operations that can compensate for that, and you need a lot of empty space. I've made a chart. The NAND storage is made up of physical blocks, and each block has a set of what are called pages. And these pages contain memory cells like we looked at earlier. The pages can't just be overwritten if you want to modify the data in them. The data has to be written to a truly empty page. It can't have anything stored in it. Older styles of flash memory and slower devices will clear the pages when it needs to access them. But having to clear before the writing process is slower. And manufacturers don't want their SSDs to be slower. They want the drive to be fast. So I'm just going to break down how one of these newer SSDs, some different ones, different manufacturers handle it different ways, may be handling that. The first step, we'll look at the chart here. Let's look at block 1 where the arrow is. You can see it contains page A, which is valid data, and it has some empty pages in that. Then block 1 gets some more pages written to it, and it has some data that needs to be modified. So a new version of that previous data gets written to the block. So now we have a whole page that's essentially invalid because there's a new version of it. So it's just taking up space where valid data could be written in the flash storage. So it's not something the drive has interest in keeping around. And then because block 1 is full, we can't write to it and we can't modify the data before erasing it. So the drive will automatically copy the valid pages to block 2 without the invalid data in it and leave that empty space that was once invalid data. So now block 1 can be cleared and is ready for writing to take place, and you don't have to wait for clear space when you need to do a writing operation. These last 2 steps that I've described are called active garbage collection, and they're increasingly common on fast SSDs. In the past, a lot of this was tied, and a lot of these processes were tied to trim or unmap from your operating system, where the operating system is telling the drive, this is invalid data, go ahead and take care of it. But these last 2 steps are generally things that drives that are very fast now will do internal to the firmware. It's a non-OS conscious process. It's something that your drive's internal firmware and controller will be doing in the background. So once the data is thought to be needed by the drive's trying to push it out of there. So in deletion cases, or even some cases of corrupt firmware on these increasingly fast drives, while it's great for daily operation of your SSD, it can create a semi-no recovery scenario if the drive is either wrongfully or because of a deletion tried to push that invalid data out to make space to write fast. Let's move on to some devices we're all familiar with, embedded storage. There's a huge amount of personal computer users today who go easily without using a device with a removable drive in it for a long time. Smartphones, all the devices people commonly use every day are embedded storage devices. Tons of people are switching to thin form factor laptops and even tablets to get work done. I'm sure we've all seen people sitting there with an iPad using it in the way in the past a laptop with a removable drive would have been used. Because these are some of the most common devices today, they've been turned into some of the most secure devices today. They have user data on them. It's phenomenal because personal data in that hardware sense can by and large be pretty safe. And if they happen to find themselves in a situation where there's damage to the device, sometimes the user can't get into their own data. This audience knows this more than any audience. I'm sure a lot of you know this, but I'm going to go over it anyway. What we often refer to as the CPU of a lot of these smartphones is actually a system on a chip. It's an SoC. And so it combines a huge variety of functions that your device needs to work in a greater capacity than what a CPU could just handle. So the chip has RAM integrated. It has essentially things that would have been other hardware in the past all in one package. So though we're calling it the processor or the CPU, it's an SoC, system on a chip. And one of these functions that is incredibly common in these chips is security. And the way they implement this is generally with what's called an eFuse array. So how is every CPU on these devices unique? Well, when they make them in the fab, they have an array of fuses that are all set by default, just going out, and then they individually use the fuses for burning them out in the silicon to serialize essentially or make each CPU unique. And so that becomes essentially your hard key. This ID function that they use with the eFuse array it can be a serial number and it can be an encryption key, and everything else in the device can be checking with that hard key to verify that you're using the right CPU to gain access to this data. This essentially means no original SoC, no data. In some cases, there's even dedicated secure coprocessor. So Google has a chip called the Titan security chip, which is a coprocessor that just works with encryption strings. And if you need to decrypt the devices, you're going to need the original hardware. A lot of times, too, the device can be reset. And it's not like a deletion case on a drive that just has the data written to it. This is all encrypted to those keys that get reset when the device gets reset. So if you reset those keys in a security coprocessor, that's like can be sometimes even just 8K or 16K strings of data that get erased that you no longer have access to the data that's encrypted on the storage with. Another implementation of this is discrete TPM, trusted platform module, which I'm sure a lot of you encounter as well. And these chips are important for verifying that unwanted access to your data on your firmware is not taking place, that you're not having some sort of firmware attack on your device. But they also complicate things if you have failing storage media and can't boot your device how you normally would to gain access to them. Outside of that, as we all know, if that chip is destroyed or missing, there's sometimes no other way to access or unencrypt this data, and it becomes a non-recovery scenario. Please don't send us iPhones with the CPU missing. I just want to go over real quick here what I personally and some of my colleagues are predicting as the future of some of these scenarios. So how can we turn some of these scenarios into possible recoveries? Well, NAND cell degradation is a pretty definitive scenario in most cases if the NAND cells are truly failed. And breaking encryption to this level would require quantum computers and a ton of time we don't have. So we're looking more into the physical aspect of these technologies. We see a lot of catastrophic damage taking place on embedded systems with security devices that are implemented into one chip. Toshiba Kioxia manufactures some really great drives, and they make one chip BGA NVMe drives all the way up to 1 terabyte. And it's in a tiny little package. These storage devices are smaller than ever. And to get access to them, work is going to have to be smaller than ever. So let's just take a look really quick at how a chip is constructed so we just have a reference for that. So here's a chart I prepared that shows the inside of an IC where the silicon die, which is the piece of silicon that's actually responsible for the functions of the chip, is bonded with a tiny gold bond wire to the substrate, which is the rigid part of the chip that interfaces sort of with the outside world. So you can see it's all put in a package there, and that bond wire is going from the actual chip to the substrate on the outside of the chip. And it's all put in something like plastic, epoxy, or glass, some sort of packaging material that we might see on most ICs. And in the events of catastrophic damage, we can see mid-span wire breaks, which is essentially where the wire breaks from stress or electrical overstress is very common in the middle of those bonds. Disbonds, that's where the wire actually separates from the IC die at the bonding point. This is pretty common under stress. And lifting, where the stress lifts the wire connections from the substrate and the die, and then you just have a wire that's not connecting anything to anything. These package failures are where the silicon may still be functional. And so that's what we're looking into. Package failures where the silicon chip on the inside may actually be functional. I have some x-rays I prepared here. This is an example of a common packaging failure we see on a storage chip from a laptop
that I'm sure many of us have seen failed storage chips on. On the left, we have the failed IC that's been damaged by the wrong voltage going into it. And on the right, we have the same chip, but only functional. And what we have here is essentially a bond that has like a mid-span break. The middle portion of the wire is broken.
I'm just going to go ahead and highlight it here for you to take a look. This bond right here, notice on the right side how it's fully intact. You can see that white line connecting point to point inside the chip. Over here, where we've had electrical overstress, it goes point to point, and then the point's there, but where it is in between is not. And so this is something that we've encountered and been able to take a look with our x-ray machine inside and identify as a failure. And so is the idea go in to the chip, etch it down, decapsulate, and just repair that bond? Or is the idea to decapsulate and essentially repackage temporarily the IC? And the idea of just, taking it out, putting in another, it sounds simple, but there's a whole lot of thought that goes into this. This is something that they do in failure analysis in fabrication places. If they have a chip that fails, they're going to decapsulate it and take a look. Why does it fail? That's generally for quality assurance or for a little more research. But we think we can sort of bring this into the data recovery world. They use a lot of really cool tools. I love really cool tools. They use IR imaging. That's a big one. And a lot of us use that in the form of heat signature reading. They have incredibly advanced thermal cameras that get to such a level that we don't have, that take a look directly at the silicon. They can see essentially the individual etchings into the silicon and identify what's going on at a thermal level with those. There's also electronic and acoustic microscopy. So think about scanning electron microscopes, taking a look at these connections to really get eyes on what's going on in that beyond what we can do with just a standard ocular microscope. And same with acoustic, using ultrasound to take a look at what's going on there. Then the other thing is going to be, how do we get into that chip? There are some people who are doing great things with laser decapsulating, and a lot of it is for research purposes, taking a laser etching machine and etching down a chip and trying to get into that package. Traditionally in failure analysis, it would be a chemical decapsulating, using some form of acid that melts away the outside of the chip. But moving forward in data recovery, there's going to have to be a conversation is how do we get into that chip without harming it, which is easier said than done. These are very sensitive devices. Another aspect of it is finding out what's actually wrong with it from a microprobing perspective. So they essentially have, it's a giant machine, but it's micro probes. So think of multimeter on a micro scale for actually directly probing the silicon. So if you're doing board work, think about the whole board. Now that silicon chip is your board. You're moving into the next level. I personally believe if something can be put together, it can be taken apart. So moving into the future, how are we going to go on that deeper level from the chip on board work, replacing the chips, from doing board work to doing chip work, to working inside of these? It's going to be a necessity if we want to get data off of some of these devices. And I think we're going to see really great things. And just a brief aside, I've been incredibly impressed with what I've seen at this show. I see that everybody here strives for excellence in their particular field. And I have no doubt that this kind of thing is going to be in the repairable future all of you are creating. I'm very excited about that. Go ahead to DriveSaversDataRecovery.com if you want to learn more about the company.